Hi Hassan, this is just an idea at the moment, but maybe one of the biggest problems from what I can see that we're having with gradient free is, could we produce a vector map of the landscape of any function? And the answer is this, as you see in front of you here, these arrows here, is a vector map. How would we produce that? Could we produce it with just maximum tracking? And I think the answer is probably not. So how could we do that? Well, let's have a look. Well, my first best guess is we use a local operator. So what does a local operator mean? Well, it means maybe that operator is centered on a particular point, the center point of that operator. But maybe that operator center point isn't used in this local operator anyway. And in fact, the points that are used are the local ones next to it, and in fact adjacent to it, which is above it, to the right of it, to the left of it, and below it. Now I've drawn that up over to the right here, as you can see, but now I've weighted them. And I thought, how could you ever weight a gradient operator so it would show you the direction? And then of course you and I remember the S-plane and the J operator. We know that when we map it, and here it is here up here on the top left, wherever we put the Ji plus J, it will arrange itself in a J-plane, and that will give us a direction. So what does that mean? Well, it means if it's in the imaginary plane, it will go from top to bottom. If it's in the real plane, it will go from left to right. And if it's in between, it'll start going in between those planes here. So maybe weighting these adjacent points, because you're only going to sum 4, dependent on the J weightings. So the one to the right tells you on the real line, so it's just weighted plus I. The one to the left is in the negative real plane, so it's just weighted minus I. The one 90 degrees to this, above it, is plus J, and the one below it is minus J. So this mirrors this imaginary plane that we see here. So what would that do then? Well, let's just have a look at how we could extend this first. So you could extend this, because one of the things I haven't said really is that J operators for gradient tracking, gradient estimation, gradient free estimation don't have to be point based. They could start for speed of point base, and then they could move on. So you could take the J across the whole state space, and we've got that to the top left. Or you could start using areas, symmetrical areas of different regions in the state space, and weighting them with the plus J minus plus I minus I plus J minus J. Or you could bias it. So I'm not saying any of this will work, but let's go and have a look at this in an Excel spreadsheet. So here's an Excel spreadsheet, and I love this. This is something you always like to say when you're recording, that I prepared earlier. So what does it do? Well, first it weights particular pixels, particular function points, a tuple say x, y, z, and it weights them using the J imaginary and real weighting that I've got here. So if we look at a simple flat surface that has a surface at a very local area, and the surface measures 0 all the way around the points, we get a imaginary sum of 0. Okay, let's say we just move the level up. So the level's changed, but there's no gradient. So the local area is 1, 1, 1, 1. And again, the local imaginary complex sum is 0. Now let's move on. Now let's say that we put a gradient on that plane, and it's going to the east, which is the I plane, plus I. And we're going to put a gradient which goes up a factor of 2 from this direction, from basically left to right. And you can see it's done that by the weighting I've given the local pixels. And then this picks it up. This actually does pick up that the arrow, and I haven't drawn this up yet, So you'll see some of these I've drawn up as arrows. So let's go down and show what this happens now with vector mapping capability. Now you see, if we look at this, the gradient's going up the j-plane, so it's going plus j, and it's going a weighting of 2, gradient of 2. And you'll see that when we map this with an arrow, it's actually going north. Now if we look at this when the gradient's going minus j, we'll see that it's going south. And now if we map this with a gradient going west, so the gradient's going to the left, we see it's minus I basically. And then the other way, which we've done here, I think we did it up here actually, up here you see it's going that direction, but I didn't put the arrow. There's an arrow there that goes from left to right, sorry. So now can we actually look at in between gradients? Can it map gradients in between these orthogonal points? And the answer is yes, it can. If we start putting a gradient that goes northwest, and here we have it, 2, 2, 1, 1, it will actually map it. Minus 1 plus j. So it's in the plus j region, and it's going minus. What about going the other way? Well, this is in the plus 1 region, which is this way, and it's going minus j. So maybe, I'm not saying this will work, maybe this is a useful tracking device. So how would we use it? Well, maybe, as I said, what we could do is start tracking gradients, which might be more useful than tracking minimum, but I'm not sure. Would it be useful to then map the gradients? Well, in this one, where we're starting to map a vector field of the gradient where the gradient is possibly in the middle, it might be, because you might be able to then jump across state space faster. But I'm not saying it is, because all this is a possible hypothesis. So let's go back to the initial slide and say, what is the hypothesis then? Well, the first hypothesis here is that gradient tracking, let's correct that, gradient-free tracking is a useful mathematical function to perform. Is it? Well, it's not as time-consuming as calculation of gradients using automatic differentiation with either forward or reverse accumulation. Does it help us, and will it find the maximum? Well, it probably will do if you remember that the points around the maximum, it will tell you there's a gradient. When you're at the maximum or at a minimum or on a plane, it will tell you there's 0. So when you get to a maximum, if all the points around it that are going downwards in gradient are symmetrical, then I would think it would give you a 0. Whereas if the points around it are asymmetrical, it might not. So I guess what I'm really saying is it's an idea. It's an idea to try and get gradient information out of point information. It's an idea that uses this concept of the S-plane, of imaginary numbers. And it's an idea that might be useful, but I don't know. I guess what I'm really saying is, what do you think? Do you think using a gradient-free local gradient estimator would be useful? And I'm not sure. So I'll leave you to think about it, and maybe we'll have a chat about it next week. I'm just going to put this on YouTube for you, and then I'll email you. We'll see how it goes.